I will start this presentation with an overview of the theory and the implementation side of the lattice electrokinetics method. And then Ingo will do the second half, where he will present all the new physics and exciting phenomena that can be simulated via the lattice electrokinetics method. So first off, what is the electrokinetics method, or EKIN, is what I will call it from now. It's a method to solve problems that include charge transport in solution. So if you see the example on the bottom left, we have like a dissolved droplet of ink that flows around an obstacle, and that can be described on a continuum level. If the droplet is charged, then we also have electrostatic effects. So electrophoresis is the transport of charged solutes driven by an external electric field. Interesting effects, of course, also happen when we do not only have a charged solute, but we also have colloidal particles in there, or polymers. For example, if a polyelectrolyte, then the polymer will be charged, and also it will dissociate ions into the solvent. So you will have both charged solvent, both charged solute, and charged colloids. And the interplay between all of them will be very interesting. And also, if you have the boundary conditions that allow it, you can also treat catalysts and microswimmers, but that part will be detailed by Ingo. The physics that govern these effects is the hydrodynamics, because it all happens in a solvent, electrostatics, because the dissolved species are all charged, and diffusion, because we're still dealing with microscale phenomena where molecular diffusion plays an important role. So you have already learned methods on how to treat electrostatic interactions and hydrodynamics in this very school. The question is, why do we not just use them? I mean, you had the tutorial just 3 hours ago, where you could use explicit ions with lattice Boltzmann hydrodynamics to treat the electrophoresis that I was talking about. One of the problems is that you might not be interested in all the details that you resolve with your particle simulation. For example, if you look at a single ion and the scale on which it relaxes from the Brownian hits that it gets from the solvent, you will get out a number that's like 10 to the minus 14 seconds. But for your large-scale phenomenon, in which you just want to see how, for example, a colloid moves in a fluid, this is not an interesting length scale. You're interested in the scale in which the debye layer around the colloid relaxes and then evolves over time if the colloid moves, for example. So that's a good 6 orders of magnitude slower. And probably you want to get away with a method that just lives on that very much larger time scale. Also, not only the time scales are very different, also the length scales are different, because if you look at a single ion and the colloid, then usually the colloid is much larger than the ion. So if you want to simulate the whole system, you need many ions per colloid, which is probably not what you are actually interested in. Next problem is if you treat particles and they are integrated with a thermostat, you end up with stochastic data. So for the observables that you're interested in the end, you have to average over lots of time steps, lots of configurations to get to the effective parameters that you're interested in. And of course, just if we want to have a large system, we need many particles, and at some point it becomes computationally infeasible. So what do we do to mitigate this problem? We go to a mean field approach, which means we replace the idea of having individual ions in, for example, this channel here, to a density of ions that moves in this channel. We can then use efficient solvers for the diffusion, advection, and electrostatics of that problem. And the grid size that are needed to resolve this problem are much larger typically than the size of a single ion, because the density variations are often on a longer length scale than the size of a single particle. Also, if you want to have many ions in the density, that just means that your number is larger. That doesn't have anything to do with the computational time that you need to solve your equations. Of course, this doesn't come for free. So if you go to this mean field approach where you replace individual particles with a density, you lose all microscopic dynamics that underlies this density, and you cannot resolve any correlation effect. So for example, excluded volume, because since there are no particles anymore, you cannot have the effect of particles jamming into each other or not being able to occupy the same space. And especially for dense suspensions, you will run into problems where these effects are not negligible. But let's say they are, and continue on with the equations that we need to describe this effective mean field approach. So first of all, what we're interested in is densities of dissolved species. This is the rho k over here. Usually you have many k's, or at least two. For example, if you have sodium chloride, then you would have one density for sodium and one for the chlorine. This is just the continuity equation that you're all familiar with. And it says that the density at some point can only change if there's a net flux into that point or out of it. So that no density can be created or destroyed at any point. This changes if you want to have a look at reactions, because then you can convert species into each other or just produce new ones. But that is a point that we will look at later. Now, this is all fine. If you know the fluxes, then you can compute the densities. But how do we get the fluxes? The first equation that we're going to look at is Fick's law, which states that there is a flux in your solute if there is a gradient in concentration of that solute, which means solute moves from high density to low density. And the proportionality constant is here just the diffusivity of that single species. You will have as many of these equations as you have species, which are at the moment independent. Since the solutes are charged, they will also feel electrostatic forces. So that's the next term that we're going to add. So down here we have phi is the electrostatic potential. Its gradient is the electric field. If we multiply that by the charge represented through the density, so the number density times the valency, so how many charges are carried by one ion, and then the elementary charge E. So this part in the back here is an electrostatic force. And then the diffusivity over kT is, by the Einstein relation, the mobility of the species. So simple terms, flux is mobility times force. And this is kind of where the coupling comes in between the different species, because this phi will be determined by all the species that are in the system, because they interact electrostatically. Also, and what we have to think of is that this is not in free space. The advection and the migration, the diffusion and the migration takes place in an underlying fluid. So the solvent can also move, which is represented here, that we add the velocity of an underlying fluid to our flux. So in the end, we kind of expect this picture to happen, where we have diffusing species that also set some flow in motion. Now, how do we deal with the electrostatics? We know that we need the electrostatic potential to calculate the force that our ions feel. So the first idea that we have is, okay, let's say we know already the density of our ions, because that's our target function that we're looking for. Then we can calculate the electrostatic potential via Gauss's law. Of course, we don't have the number density in here. We have the charge density here. So to get to the charge density, we have to do the exact same thing that we did for the forces before. So for each species, we multiply with each valency and with the elementary charge. And then if we plug this rho charge in here, we end up with the equation below, which looks a bit complicated when it comes to prefactors, because we have introduced the Bjerrum length here, which is kind of the length scale at which electrostatic interaction becomes comparable to thermal noise. So this kind of gives us a measure of how strong the electrostatics are in that system. If you plug in the number for water, you will end up with something like 0.7 nanometers. But this doesn't concern us all too much. What's important is that we have a Poisson equation that says the Laplacian on the electrostatic potential is the sum of the number densities. Next up, we have the fluid that we have to solve, because we need to add it to our advection problem. I'm not going to talk too much about how to solve fluid dynamics here, but because We've seen a lot of the Navier-Stokes equation already, and we will see even more tomorrow and the day after. So all that we need to know is that it comes from mass and momentum conservation. We usually have Newtonian fluids, which means we just plug in a constant viscosity nu over here. And we have an incompressible fluid. That means the density of the fluid does not change in space and in time. So the continuity equation for the fluid goes to 0 here. And then what also has to happen is that not just the fluid affects the particles or the ions, also the ion density affects the fluid. So I have this little video here where we have particles in a channel. We apply a force to the particles, and then by friction, the little arrows are the velocity of the fluid. So we set the fluid in motion by putting a force on the particles. And we see that the expected Poisson profile develops, even though the force on all particles is the same. It's just that the hydrodynamic interaction makes it such that we have no slip boundary conditions on the end, and then a maximum in the middle of a parabolic flow. This video is only here for illustrative purposes. We still, of course, only have a continuum fluid. We do not have ions in it. But the idea to get the force on the fluid is the same. So first of all, we get all fluxes that have nothing to do with the fluid, so the diffusive and the migration flux from the electric field. And then we calculate the force on the fluid, which was here as our external force added. We get that from scaling the flux with the 1 over the mobility again, because 1 over the mobility is the friction that this flux would produce on the underlying fluid. So now we have them in all their beauty. These are the equations that we need to solve. We have Nernst-Planck to bring everything together. We have Poisson to solve for the electrostatic potential. We have Navier-Stokes to get the fluid field. And then we have the back coupling so that the whole method is consistent. Now, how do we solve this thing? For this, we have the efficient lattice electrostatic algorithm, which was developed by Capuani in 2004, but has since been improved and is now in something like this form in Espresso. And I will not go over how it's been in the past. I will just lay out how the algorithm is implemented right now. So the first thing that we have to look at is we want to solve for the densities, and for that we need fluxes. If we want to update our densities, we have to discretize this equation somehow. So the first thing we do is we choose a grid, and then we integrate over one grid cell both sides of the equation. For the fluxes, we can apply Gauss's divergence theorem to turn the integral over the volume into an integral over the surface of that volume. Physically, that's basically the same that we already said with the above equation. If there's a change in the density inside of this volume, then it has to come from the fluxes that enter or leave that volume. So if we do that for a single lattice cell, and we assume that inside the lattice cell the density has to be constant, then this volume integral just turns into a constant times the value in the middle of that cell. And here the same, we say, okay, across each link that connects a cell to its neighbors, we have a constant flux. And then also the fluxes reduced to a sum over all neighbors times the area. Also, we have discretized the time derivative in the standard way of having the next time step minus the current step divided by dt equals to something like a derivative. Of course, if we say we have fluxes to all our neighbors and we have some kind of an area here, it gets a bit tricky if we talk about neighbors that are not face neighbors. So if you think of a dice, you think of the 6 obvious neighbors on each face, but then you can also put neighbors in the corners and along the vertices. Then the definition of that area is a bit tricky, but it can be worked out. And this formula in general is also applicable if you have non-face neighbors. Okay, so we have this. If we have all the fluxes, then we can update our densities. How do we get the fluxes? So the first thing we're going to look at is the fluxes that come from diffusion and the ones that come from the forces. I'm also going to only show the following equations in 1D, but if you want to solve the whole problem in 3D, you just have to more or less trivially extend it via the y-intercept direction. So the first thing that we note is we need the fluxes on the links or on the faces between adjacent nodes. So we are interested in the value of the flux at x plus dx over 2, this value over here, in between the nodes that we're looking at. And if we want to discretize this equation above, then we get this rather scary looking expression, but it's actually not that complicated if you think about it, because this here is just the easiest way to approximate a derivative between 2 points, because we just take the secant here at the function. This is what we do for the two derivatives. So we do that for the density derivative, and we do that for the potential derivative. Both of them are just finite difference. And then the density back here is just linearly interpolated between the two nodes that are neighboring the link that we're looking at. So this looks scary, but it's actually rather simple. Now the question is, how do we get this potential over here? So we somehow need to solve electrostatics. For that, again, we look at the 1D idea. We have the second derivative of the potential is minus the density. We discretize the second derivative. For the first derivative, we need at least 2 points. For the second derivative, we need at least 3 points. So we're going to take 3 and do this numerical derivative here equals to rho. And then this is an equation that involves 3 phi's and 1 rho. If we do that for the next node, we will again get an equation that involves 3 of the phi's in the row, and again, and we get as many of these equations as we have access, so lattice nodes. And in the end, we get this system of equations here, which we can write in matrix form. What have we gained through that? Because this still looks like a difficult thing to solve. But now we just have a matrix equation, and probably since the 8th grade, you know at least one method how to do it. You would go there and do Gauss elimination until you can solve for every of the phi's here. You can, of course, do this exact method, but if you want to be a bit more performant, you can also do iterative methods, and then you just have to say, okay, I want this much accuracy, so I'm willing to spend this amount of time into getting the solution to this problem. But this is a very well-known problem, and many solutions or solution ideas exist for it. What we can also do, if we have full periodicity, is use the Fourier transform to solve the Poisson equation. Probably many of you already have done that on paper, to use a Fourier transform to solve differential equations. We're just using the discrete version here. So we start again with a discretized version of our differential equation. Each term gets a Fourier transform. We rearrange all these terms. We make use of the fact that these guys here are orthogonal. So the equality here has to not only hold for total sum, it also has to hold for each summand. So then we end up with this expression here in Fourier space, which is just an algebraic equation. So if we know the row hat of k, we can just multiply it by this factor and get the phi hat of k back. And the neat thing about the Fourier transformation is that they are not just used here by us. It's a very widely used algorithm. So there are efficient methods already implemented. So if you want to implement it yourself, you would basically just code this part and let the Fourier transformations and also the back transformations be handled by some library. So you can kind of count on the fact that this already has been thought of by other people and is very fast. Now we have the diffusive part, we have the forcing part, we have the electrostatic potential. The last thing we need is the advective flux, so the underlying fluid. For this, we use this volume of fluid method, where we say, okay, we have here the black cell is the one we're looking at, and we want to calculate its fluxes to the neighbors. For that, we take the velocity from the fluid, which is the red V here, and we displace the black square to the red square, which is just the velocity times dt shifted. And then we see how much overlap is now between the red square and the neighboring cells of the one that we looked at. So the green, orange, and purple area. And the flux across this link, for example, so from here to here, is now the green area minus whatever would come from the virtual displacement of the left box here. You can see now that we get a lot of neighbors. So if we displace the black cell somehow diagonal, we definitely get also this orange bit here, which goes to the corner neighbor. In 3D, you can see how you now have all the 27 neighboring cells that you have to look at. But in principle, this can be worked out for each link between neighboring cells, and will guarantee you that you do not lose density because you just move it from here to here, and yeah, it gets subtracted here and added here. Now the fluid itself, also we have had talks on lattice Boltzmann, and we will have more talks on lattice Boltzmann, so I'm not going to spend much time on it. We just have to note that it can be done. It solves the Navier-Stokes equation for us, and we use the same discretization as for all the other quantities that we had, like the electric potential and the densities. In that way, this method here will work out perfectly because we know all the velocities at the center of the density cells that we had in the beginning. Okay, now no problem is complete without the boundary conditions. So we kind of have solved our bulk equations now, and the question is, how do we couple that to any boundaries that we have? So if we have just fixed objects, like a wall, for example, or even the colloids that we place in there, we would use for the solute a zero flux boundary condition. So you can imagine here, I just drew it for the advective part, but it holds for all of them. It's just we compute somehow a flux that would go into the wall, but then there is a wall, so we just say, okay, this link has to have zero flux now. It's 1 degree of freedom, we have one condition, so this is already done. For the fluid, we have to use the classic bounce back to get the no-slip boundary condition. Bounce back is a bit more complicated than just setting the flux to zero, because we have one condition that the velocity has to be zero, but LB has more degrees of freedom, so we have to make some choices there. But I think that will be, or already has been detailed, I'm not sure. Anyway, if we have objects that are not fixed in space, we have to use some kind of moving boundary. So if we have large objects compared to the lattice size, we have to use this moving boundary scheme, of which Inge will talk more later, where you kind of create and destroy boundary cells based on the movement of your large object. Or if you have smaller objects, then we do the friction coupling that we already did in the tutorial today, where you say, okay, I interpolate the velocity at the position of the particle from the neighboring nodes. And then via friction, I calculate a force on the particle and also a force on the fluid. We can also have more interesting surfaces that are catalysts. So there you could have an influx or an outflux of species, depending on which species are present and which catalyst you want to model there. In general, this is just a non-zero flux boundary condition. How do you actually do it? If you want to simulate a system, you would, of course, first use espresso, because it's relatively simple to set up the electrokinetics method, and all the coupling to particles is already done for you. You can also use different implementations, for example, in Valbala or in PyStencil, but I think I don't have to talk about them much because they will be detailed tomorrow in the respective talks. Now that we have the method secured and we know how the equations work and how to solve them, I hand over to Ingo, who tells you what kind of physics we can get out of them.
Okay. So now that we learned how the electrokinetics method works in general, yeah, I'm going to show you where it can be applied and what extensions need to be done to the model to apply it in some other cases. So first things first. As you saw in the tutorial, in the Boltzmann tutorial today, you can normally you can use MB simulations to render so those colloid solutions and with ions, so that you can basically get a density profile from that if you simulate long enough, so that you can so that the ions are equilibrated into the system, and then you can practically measure if you measure over a long time, you can get the exact ion density out of the system. However, these simulations take a long time because there are many particles and it's a large system. Using the electrokinetics method for that is quite fast. Well, so you can get for such system the solution of the density profile in a matter of seconds. So you see that so that the density accumulates of the anions of the counter ions accumulates around the colloidal particle, which is in this case represented by a non-moving boundary, and far away the density is almost zero. So that you now that you with the electrokinetics method, you see that you can show those accumulations of densities or depletion of densities. You can also use them in a more sophisticated way using, for example, electro-osmotic flow. So electro-osmotic flow is basically you drive flow field due to electrostatic interactions. And normally, let's say if you have an electric field underlying acting on a neutral solution where ions and counter ions are equally distributed, one would say if the counter ions are attracted to anions, to the cathodes, and the anions are repelled by that, that would gain a net zero force. However, if you put in an asymmetry in the system, for example, like here, we have this asymmetric pore, where it's easier for the ions on the right side to move to the left of the pore than from the ions on the left of the pore to move to the right. Then you can get a net flow out of it. So basically, these anions are get attracted to this cation here, cathode, and here move through there and then get attracted to the cathode on the other side. So basically, the system is periodically continuous. While the anions move through the pore on the other side, however, this movement from left to right is more slowly, and therefore the net flow on the net force on the fluid is also more to the right. However, because there's also this flow, the reverse direction where the flow can happen, you see that there's these the vertices that happens, and also if a particle basically is like here in the fluid, it also moves into the right, while the net movement of the system moves to the left. So you need to so you need to take note of this. These systems are interesting because on these sizes, where we are in nanopores or something like that, or porous media, normal fluid pumps are very much ineffective. So we need other methods to get a controlled fluid motion, controlled fluid into motion. Okay, so the next thing is that we want to look at one extension to the model, as Christoph already mentioned, namely reactions. So reactions in the electrokinetic model are mainly done by two things. The first thing is that you can use bulk reactions. So the reaction takes place everywhere in the system with a rate defined via the takes place anywhere in the systems. The reaction itself couples the densities of the different species together in a way that, for example, if you have a reaction from species A to species B, then species A depletes everywhere, and species B gets created everywhere. And this rate of depletion or creation is based on the density of species A. I mean, so those species can be coupled in that way. And it's also not these reactions is also no, so it depends on the local density of species A, not on the global. The other way these reactions can happen is not only in the bulk phase, but also as a surface reaction. So basically, you have a catalyst, and only at the surface of the catalyst the reaction can take place. Like platinum absorbs hydrogen or something like that. And in that way, you get net flux into the boundary of species A and the outflux of species B. Well, and yeah. Okay, so now where can these be used? These can be used in, for example, microfluidic reactors for catalysis. One example would be basically the catalyst at the exhaust of a car, so where it's consumes the reactive exhaust gases and make them inert products like water or carbon dioxide. Those systems can be nicely simulated and see where those carbon dioxide is formed and how can be mostly optimized so that the flow gets more across the surface of those platinum reactors. And other things is that you can also have catalysis with molecules. So molecular catalysts are normally used in reactions where they are always in the same phase as the products, as the substrates they are reacting with, like, for example, gas or fluid phase. And therefore, if the reaction takes place, the whole system, the density of the substrate that is reacted reduces constantly. However, it reduces constantly, and this also leads to a lower turnover of the reactions when the density gets low in the end of the reaction. However, if you put those molecular catalysts close to a wall or bind them to a wall inside some microfluidic devices, you can basically set the density of the reactions at a constant high rate. Therefore, the turnover is always at a certain, is always that high. And the thing is that what you can do with the electrokinetic method is you can try to optimize where you can put those catalysts so that you can basically maximize the amount of species A that gets accumulated at the catalysts, and also optimize in a way that the products that are created, in this example B and C, are moving away from the catalyst as fast as possible, so that the catalysis can be driven in optimal circumstances. Okay, another way where catalysis can be of importance is microswimmers. Microswimmers are basically active matter. So they propel themselves forward using different mechanics. And this case here, the mechanic underlying this movement is due to chemical reactions and an asymmetry of the particles. Active matter will be also taught, I think, on Thursday in more detailed view, but not on these catalytic microswimmers. So how do they work? Mostly we have an hydrogen peroxide solution to them, and there are two different reactions taking place on both sides of the catalyst. So on the first side, we see that the hydrogen peroxide gets reduced to oxide and hydrogen atoms, hydrogen ions and electrons. the electrons move through the particle itself, and the hydrogen atoms, ions, flow are in a fluid. And on the other side, this hydrogen peroxide reacts with these products, created products, to water. Okay. And one theory why these catalytic microswimmers move in a way is that these ions, these hydrogen ions, they move from here to here and gets depleted here. So we have basically a high amount, a higher density of hydrogen atoms here, and a low density of hydrogen atoms here, ions, and therefore we have a resulting electric field. In the inside of the catalyst, we have the electrons, which basically give a charge, and then we have a charge in the ion, in electric field. Then we get a force on the charge on the particle acting, which propels the particle forward. It's kind of sounds kind of like the particle itself pulls itself on its own here out of a swamp, but this can be energetically be explained because the hydrogen peroxide that is used for the reaction at the beginning has a much higher energy density than the oxide and the water that's resulting in this reaction. So basically, we can convert chemical energy into kinetic energy of those particles. Using so when using the electrokinetics method, those 5 species mentioned here are very much pushover, so we can easily reduce them to make smaller. So basically, we say we have a reaction of species A to species B. Species B is charged, and a reverse reaction of species E to species A. Okay. Now that we have a theory how these catalytic microswimmers work, we have this self-electrophoresis. So they move itself. Electrophoresis, they move themselves via an electric field. Okay, how do this translate into simulations? So as you can see here, also there is a poster on this wall who wants to look at this in more detail. You can see that if you apply those reactions, as we mentioned, into an electrokinetic model, you can see that the densities and the densities of the hydrogen peroxide. So it's not the density of the hydrogen peroxide seen here, but the difference in the hydrogen and the density, the gradient. So you see that here it's the grade, it gets depleted, and here it gets created. Also for the hydrogen ions, we done the simulations for with our electrokinetics model and also with a finite element model. And you can see that the finite element model, which is on those cases much more exact, produces we can basically show that our model is a really nice approach to that to these results. On the other side, on the flow field, there's a little bit of a mass in the close to the surface of the catalyst, but this mass can be easily explained because while the finite element method uses a really round swimmer particle, using this in the electrokinetic method, we have basically different blocks, which from far away looks like a sphere, but these blocks are still blocks, and therefore the near field of the fluid makes it a mess if the reaction is dependent on the cosine of the surface. Okay. However, if you say, when we can simulate such systems with a finite element method, why should we use the EK anyway? However, that's because the finite element method gets only static results on on such systems, while we with the electrokinetic method can also added dynamics to the system. These dynamics, because we are using a colloidal particle which is explained by a boundary, needs to be moved in a way. This movement of this particle works basically as you learned earlier in the Boltzmann lecture, where the method of lat was introduced to move those boundary cells from front to back or back to front, depending on the movement. And we can also use a much more another smooth method where we do not have the charges, where the charges are not fully distributed distributed equal over all boundary cells, but we can also say that the charges on these boundary cells also sorry, that the charges that are on boundary cells that are close, again. That we have basically transition boundary cells that are close to the fluid. So if a cell is only halfway a boundary, then we can say it is only half the charge. So that the charge itself is on the one hand side conserved, and on the other hand side it's then not moving that fast if the particle if one cell is created as a boundary cell while the other one is removed. So now we can have these moving boundaries, and now we can see them in action. But first, let me explain what you're going to see. So we have two particles in this case, and at first those particles don't see each other. So at first both of those particles will move to the right as they're supposed to due to the self-electrophoresis. However, once the density gradient of those hydrogen ions is large enough, then the other side of the other particle sees this gradient. So, and when it sees this gradient, it sees the electric field, and then the forces on the one side is greater than the forces it uses for itself, and therefore the actual propellant force reverses, and the particles move in the other direction. So, yeah. So see, first it moves to the right, then the particles see each other, stop moving for a while because the forces are balanced, and then after some time, the flow field reverses and the particles itself reverses. It's also to note that this is a periodic boundary condition, so it's not only that this particle sees this particle, but also it sees another one on the other side with the reverse with the other reaction. So it's basically a long chain which pulls along itself. And it's also interesting to know that while this is simply a linear case for those active particles, you can also have them differently ordered or something like that, and you see that because every particle basically undergoes the same reactions around itself, the interplay between the different species created and the density gradient will have a really huge impact on what really happens when they're immersed in when there's immersion. Okay, so now from catalysis onto the next small extension that we can also do is that you can add fluctuations to the system. I mean, Christoph earlier showed that these fluctuations are usually left out of the model. However, they can be explicitly added again, and by basically adding a random flux scaled via the square root of the local density. So the smaller the local density, the higher the relative flux of the species. And system where those fluctuations can be useful are, for example, systems that are in a semi-stable state, where basically small inconsistencies can lead to a whole new it can lead to a whole new result. And one other thing that I'm going to show you is that these fluctuations have also come also in handy when looking at systems that are not linear dependent in density. So, for example, we have a reaction of 2A reacts to species B, and because the species A is twice in the substrates. The density depends also the density depends on these reactions is also is of the order rho squared. And when looking at these reactions with and without fluctuations, we can see that they pretty much that there's with reaction there's much more substrate being created in the same amount of time, as you can see here. So the red one is with fluctuations, and the green one is without. This may be important when looking at such systems which are nonlinear in density, and you don't have those fluctuations on, or other. You would simply get not the right results as the experimentalists also you're comparing with. And then you might ask, why would my model put in the wrong results? And definitely need to look at what you need to add to the theory that you're using to show that, and what is important, so that you can basically recreate experiments or something like that. So, and with that, I also want to conclude from my side, and thank you all for your attention.